Assalamualaikum warahmatullahi wabarakatuh. Selamat sejahtera.
Waalaikumsalam.
Dengar tak?
Dengar.
Okay. Okay, Bismillahirrahmanirrahim. So we are still in chapter 2. Rotational system. Okay. After we look into the electrical system and mechanical system. So rotational system is the continuation of mechanical system, where you have a mass, spring, and damper. Okay. But on top of that, the system is rotated. Okay. So it will give you top angular velocity, top angular displacement, and impedance rotational relationship for spring, viscous damper, and inertia. For this diagram, to look at the spring itself, okay, where you have a reference point on your left, and then the spring, and the spring constant at K. And there is a rotational system with a torque, okay, torque diaculus at capital T, and the angular displacement theta T. Okay, so the force in terms of the spring is shown here. Angular velocity and angular displacement. Okay, where K is equal to K theta T, where K is the spring constant, right? So the second one is the viscous damper, okay, where you have a oil, okay, inside the damper, and the viscosity of the oil is represented by the D, which is the viscosity damper constant, where the force is equal to D omega T. And when you detect under displacement expressions, it will become d theta dt. On the initial part is the J, okay, where it will have a rotational of the torque and angular displacement, which is theta T and theta, okay. And in terms of angular velocity, it is T is equal to J d omega dt, or T is equal to J d square theta dt square. Okay, omega ni is angular velocity. Okay. While theta is the angular displacement. Kan? So kalau dia rotate, tu kan, so dia akan menghasilkan sudut, okay, 90 darjah, 180 darjah, 270 degrees, okay. For backwards, minus 90, minus 180, and so on. Okay, and this one is considered as d omega dt is considered as the angular accelerations. Okay. The important thing is this one, where you Laplace it. When you Laplace spring in rotational system, you will get K. When you Laplace viscous damper, you will get ds. And when you Laplace inertia, you will get J S square. Okay. So this is one of the examples of a simple rotational system. Okay, where you are required to find the transfer function theta 1 over T1. Okay, so theta 1 is the output. And T1 is the input. Okay, so this is your rotational theta 1 and T1. And the basic mechanical rotational system is represented by J1, B1, and K1. And this one is the reference datum. Okay. Ini macam dalam electrical we call it as a 0 volt lah, ataupun ground. So for this simple rotational mechanical system, it can be represented by a free body diagram, similar to the mass, spring, and damper, where you have the free body diagram. Okay, if you still remember, you have a mass, then you have a force, then you have a spring, and the force of spring, and then the force of damper, FV, and the mass itself. Okay, so but this one is for the mechanical system. But for rotational mechanical system, it can be represented by the input. Sorry, the input, which is T1, the force, and the output, which is theta 1. Okay, the angular displacement, the directions of the rotational inertia J1. So J1 too is usually is a shaft. Okay, is a shaft steel. Okay, that rotate. Okay, clockwise or anti-clockwise, right? So it applied this inertia applied in many applications. Okay, in robots, in the automobile, okay, in any electrical system that involve DC motor, AC motor, and so on.
Doctor,
So yes,
question.
please. Yeah.
This is like an axial system, right? Like it use torque and
Yeah.
angle.
Yes.
But how do in this illustration, how do you split the axle between the mass and the viscous damper and the spring? Because it's an axis, right?
We are not considering the axis, okay, like this, okay, X, Y, Z, okay. We are only follow and consider the directions of each input, output, and the rotational Laplace as shown here.
Yes.
So there is no axial. There is no axial involved in this case.
Wait, doctor. Could it be like between the mass, it splits into a like system of gear?
Of gear.
Yeah. So that way,
yeah.
they can split the axle.
A gear will be delivered after this. This one is only rotational only. There is
Okay.
no gear inside it.
Because
Okay.
it's confusing, like this mesh
Uh,
is rotating, but
yeah.
the rotation is split between two devices.
Yeah. In fact, this rotation, this initial, there is no teeth, no gear on the J1. So the next part will be a teeth here.
Uh,
Okay. There will be teeth, and this one will be connected to another another initial with the teeth. Okay.
yeah.
So it will involve the number of teeth of J1, J2, in order to for us to model the system.
Yeah. So that's how they split the
Mm,
axle. Okay. Thank you.
yeah. Okay. So based on this, uh, the input is T1. Okay. So T1 is the input. So we're going to find the differential equations. Okay. So as simple as mechanical system, the directions T1 is opposite with the J1, D1, and K theta 1. So simply you can use this formula where J1 is equal to theta 1 double dot, D1 theta 1 dot plus K1 theta 1, which is equal to T. Okay. So when you use the Laplace, okay, Laplace, you follow the previous table of slide 68. Okay. So this one will become J S square theta 1, D1 S theta 1, and K1 theta 1. Right? So from here, you just factorize. Okay. So theta 1 over T1. Okay. So it will become 1 over J1 S square plus D1 S plus K1. Okay. And of course, you can directly simplify it. So it becomes J1 S square S plus K1 J1. Okay. So once you know the value of J1, K1, and S1, D1, okay, so you can get the transfer function and the mathematical model of this rotational diagram. Okay. So examples 2.19, where we are required to find the transfer functions of theta 2 and Ts, where you have a input force here is the input, and you have a two. There is a two output, which is theta 1 and theta 2. Okay, theta 1 is the angular displacement of initial J1, and theta 2 is the angular displacement of mass J2. And of course, you have a torsion. Okay, torsion is like this. This is torsion. You have a force, then the J1 is rotating clockwise, while the J2 is rotating anti-clockwise. Okay, satu lawan jam, satu ikut jam. So the torsion macam kita apa? Macam pegang baju kan? We want to spin the wet cloth. Okay, so this where it happens in the bearing system. Okay, so this is a bearing. Okay, okay, so is a circle. We have two circles. One is inside circle, the other one is the outside circles. So between these two circles, you have a ball. 1, 2, 3, 4, 5, 6 balls. Okay, it depends on the size of the bearings. If the bearings is a big bearing, so you have many balls inside between the outside circle and inside circle, right? So what is the function of the bearing? So bearing is one of the machine element. You have a very big machine, for example, a car. So you have a machine element where bearing is part of it. So where is bearing located? Bearing located at the rotating shaft of the car. So if you have a four tire in one car, so you have 4 bearings. Okay, 2 bearings at the rear part and 2 bearings at the front part. Okay, so this bearing is constrain relative motions to only the desired motion, and it reduces the friction between the moving parts. So you have the wheels that rotate, and then the shaft that rotate the tire. So between the shaft and the tire, okay, tire is the load, the shaft is the actuator. So between it must have a bearing, because there is the frictions between the shaft that rotate the tire. So this friction can be reduced, okay, can be reduced by using a bearing, okay. So in the field of solid mechanics, torsion is always happen. Torsion is the twisting of an object due to the applied torque, and it is expressed in Newton per square meter or Pascal, okay. So I want to ask Farid Rizwan. Hello, Farid Rizwan.
Yes.
Are you there?
Yes.
How do we know that the bearing is the good condition and bad condition? Soalan quiz, yesterday quiz. How do you know that the bearing is good condition and bad condition? Tak tahu.
I'm not sure. Sorry.
Not sure. Still sleeping. Aisha Akram.
Yes, Prof.
How do we know that the bearing is the good condition and bad condition? Tak tahu. Maisara? Maisara?
Yes, Doctor.
How do we know that bearing is a good condition and bad condition?
I'm not sure, Doctor.
Tak tahu. Siapa yang tahu? Who knows?
Can I guess, Doctor?
Yes, please.
I think you just see the balls if it exists there and if it's loose or not. Then put the shaft and rotate the bearing itself. If it's rotated loosely, then it works, I think.
Oh. So how do we know is the good and bad bearings? Bad bearings need replacement. Good bearings no need replacement. It's based on the sound. Okay. So bad bearings, when it applied to the car, the wheel and the tire. So when the bearing is bad, okay, so it will give a sound. Okay. When you drive a car, so the bearing will give a sound. So many sound, okay, give you sound, annoying sound due to the frictions between the shaft and the tire. But good bearings, there is no sound because the friction has been absorbed, okay, has been eliminated by the bearing machine element. Is it okay? Okay, Farid, clear.
Boleh bro.
Faham, eh?
Faham.
Okay. So next one is obtain the schematic form from the physical system by assuming the torsion acts like a spring concentrated at one particular point in the rod. Okay, initial J1 to the left and J2 to the right. Okay, here as shown here. The damping inside the flexible shaft is negligible, can be assumed as 0. So the torsion acts like a spring here, concentrated at one particular point in the rod. Okay, so you have two inertia, J1 with angular displacement θ1, J2 with the angular displacement θ2, and the input is torque. Okay, and K is the torsion part. Okay, represented by the spring, and you have a damper, left and right. Okay, D1 and D2 with a reference datum on the left and on the right. So now we just looking at the diagram, so we can produce the equations of the force, which is represented by equation 1, J1 θ1 double dot plus D1 θ1 dot plus K θ1 minus θ2 equal to torque capital T. That is for the equation number 1. Then for equation number 2 is J2 θ2 double dot plus D2 θ2 dot plus K θ2 minus θ1, which is equal to 0. All this come from a free body diagram, which is shown here. Okay, so for J1, torques on J1, okay, torques on J1 due to the motion of J1 is shown here. Okay, J, D1 and K is opposite of the capital T, the torque. And then torques on J1 only due to the motion of J2. So we have another one which is the same direction as the input torque. Okay, and then we consolidate, okay, between the A and B. We consolidate itu maknanya kita satukan. Okay, it becomes the final free body diagram for initial one, which is T is equal to T plus K θ2 is equal to J1 plus D1 plus K θ1. Okay, so since θ2 we bring to the left, so it becomes negative. So we get equation number 3. Then for initial J2, due to the motion of J2 is shown here, where you have a direction of K, D2 and J2. And then torque on J2 due to the motion of J1, which is K θ1. Then the final free body diagram for initial J2, okay, is the consolidate between the A and the B. So you get the final one where K θ2 plus D2 plus J2, which is equal to K θ1. And you bring K θ1 to the left, so you will get equation number 4. So you have equation number 3 and 4 in Laplace transform. So you obtain the transfer function θ2 over θs as shown here. So you open all the equations, okay, and then eliminate θ1, so you will get the answer for θ2 over θs from equation 3 and 4. Further details you can refer to the book chapter 2 as I attach in the WhatsApp. So you are given a problem 30 and problem 31. This problem, without the symbol of J1, K, and D. So it's already given the value. The damper value on the left is 8 Newton meter second per radian. In the middle, 1 Newton meter second per radian. Spring value is 9. On the right one is 3. And the initial J1 and J2 is 5 kilogram and 3 kilogram respectively. So same problem as previous. Okay, so try to see. This is the problem. Okay. So for each of the rotational mechanical system shown in figure 2.16, write, but do not solve the equation of motion. You just write it. Okay, and then you Laplace it, then you leave it. Okay, so can be summarized. The figure A just now. Okay, you can simplify it to this one. Okay, and then can write straight away the equation of motions, but I didn't include the free body diagram. So can you please include free body diagram inside this? Okay. Okay, so then you will get equation number 1 and you will get equation number 2. Okay, and then from there, you don't have to solve it. Okay, you don't have to solve it, but if you want to solve it, also can. So it will become more complicated by finding theta 2 over t. Okay. And the second part, which is this one. Okay. So I shown it here. Okay. The equation of motions, which is the continuations of this part. Okay. The second part is this one. Okay. Problem 31, where you are given a rotational mechanical system shown in figure 2.17. Find the transfer function theta 2 over t. Okay, so with the value all are 1, 1, 1, damper 1, and damper also 1. So have three damper, 1 initial, and 1 spring. So by writing a free body diagram before these equations, so you will get the two main equations that represent the system. Okay, so you draw the free body diagram. Okay, for initial J1, 1 kilogram. Okay, and then you will get these equations. So how you get this part is by factorize by the matrices. Okay. Theta 1, theta 2, okay, which is equal to E and 0. Okay, so this part, we have a 2 by 2 matrices. Okay, so this is a S square plus 2S plus 1. And then this one is a minus S plus 1. And this one is minus S plus 1. And this one is 2S plus 1. Okay. So you have two unknown here, theta 1 and theta 2. So in order to solve for theta 2, so you take this part, okay, this part, put it here, Okay, and then the output path, you put it here. Okay, and then you divide by the front part, okay, which is minus s plus 1 and 2s plus 1 over 2s s plus 1. So this is a symbol of symbol apa ni? Tanyalah sikit. Najwa Atira. Simbol apa tu? Najwa Atira. Tak
Yes,
datang.
Prof.
Ya. Simbol apa ni?
Modulus.
Modulus. Modulus, I'm afraid is wrong. Is a
Oh,
determinant.
determinant.
Okay.
Yes.
Modulus is like this. -1. So you get positive 1 kan?
Yep.
But for this is determinant is cross multiply. So this one s square plus 2s plus 1 multiplied by 0. 0 minus minus. So it become ts lah, kan? This part. So this one multiplied by this one minus this one multiplied by this one. So you simplify it and you will get 1 over 2s s plus 1. Okay. Further details in the book chapter, chapter 2. So I show it here. Okay. Some of the students still don't remember, so I show it here. Okay. So how I get theta 2 over t, right? You can refer to slide number 80. And for rotational system, you can refer to the self-learning via YouTube at this channel. Okay, any question? Amir Farhan? Amir Farhan,
Yes, Prof.
any question?
No. No.
No question.
Yes.
I have question for you.
Okay.
What is the torsion?
Question is I think same is a twisted object like due to torque. Hello?
Huh?
Question is a twisted of in the object due to torque.
You ke? Go Ming Kiat. Go Ming Kiat. Tak datang. Zairi,
Yes, Prof.
what is torsion?
Torsion is more like by the twisting object. The
Twisting?
twist.
Tak dengar.
Sorry, my mic is. Torsion is about like a force due to twisting object that have been done by a torque force.
Okay lah, boleh lah. Boleh lah. Tu
Thank
dia
you,
kan.
Prof.
Alright, so we move to next one, rotational system with gears. So I believe that everybody have bicycle, have a road bike or mountain bike. Okay, so can we ask one student, Sharifa Khairunisa, the longest name in the class? Anak
Yes.
Pak Syekh ni, Sharifah. Anak Pak Syekh. Kaifa haluk?
Hello.
Hello, Kaifa haluk? Sharifah. Sharifah kat mana ni?
Saya di rumah.
Rumah, eh. So, do you have a bicycle, Sharifah?
Yes, I have.
Okay, can you explain what is gear in your bicycle?
My gear in bicycle function when going uphill, going when the gear is low, then the bicycle is ringan. It's like
Kalau Singlish, aduh. So how you change the gear when you are in the flat road and uphill road and downhill road?
downhill, I changed to low gear.
Low
But
gear.
uphill,
Uphill,
low gear for uphill. But
betul.
downhill for
High gear.
gear.
Flat road?
Flat road, don't care.
Huh? I don't care.
think, don't doesn't matter what gear.
Okay, come back to Sharifah answer. So we have a gear system. The simple one and the most affordable one is bicycle. Okay, so we have two type of bicycles mainly. One is a road bike, and the other one is what do you call that? Mountain bike. Betul? Correct? Hello? Hello?
Betul, Prof. Correct, Prof.
Betul. Okay. So gears, there are a lot of brand of gears in the market for bicycle. Okay, one of it known as Shimano 105. Okay, Shimano 105. One of the popular gear. Okay, Shimano 105. Okay, for road bike and Altegra gear system. Okay, and some brand is SRAM. Okay, there's a lot of brand in the gear system for road bike. So it used with the rotational system, especially those that are driven by motor. So we can match the driving system, the rotating, with the load. Okay, by using the gear. For example, gear with the system uphill, we need more torque and less speed. Okay, we shift the gear to the high gear, and then for level road, we shift the gear for more speed and less torque. Okay. So the special bicycles that no need a gear is a bicycle that ride by Azizul Hasni Awang. Okay, I forgot the names. I think what is the name of Azizul Hasni Awang bicycle? The price is about 500,000 RM. Okay, that bicycle just have a single gear. Okay, but it's very aerodynamic, very light, and the body and the frame of the bicycles is made from a carbon. Okay, carbon composite. So this is the structure of the gear, okay, where you have a input gear and output gear. So usually R2 is the rear gear at the back of the bicycle, and input gear is R1. Okay, so R1 is the radius of gear 1, and R2 is the radius of gear 2. And each of the gear have the teeth. Okay, have a teeth, and the number of teeth is represented by N1. Okay, gear 1 have a teeth, the number of teeth is represented by N1, and the number of teeth for gear 2 is represented by N2. So when we give a torque at gear 1, okay, T1, and it start to give you angular displacement, theta 1, and it's connected between R1 and R2. When R1 is rotate, R2 also rotate, but at the different directions. Okay, you can see here, T1 and theta 1, the direction is clockwise, while the gear 2 with the torque of T2 and theta 2 is rotating anti-clockwise. Okay, so input drive gear and output drive gear have the same concept. Okay, different radius, different number of teeth, and the directions of the angular displacement and the directions of the torque is different. Okay, clockwise and anti-clockwise. So that is for the input gear and the output gear. So the important relationships here is this one. Okay, the ratio number of teeth is proportional to the ratio of the radius. So please remember N1 over N2, which is equal to R1 over R2. And ratio angular displacement is proportional to inverse proportional to 1 over ratio number of teeth, which is theta 1 over theta 2 equal to N2 divided by N1. So we can relate this, okay? We can relate this with these equations, okay? Theta 1 over theta 2, which is equal to R1 divided by R2 and N1 over N2. Okay, so just like translational motion, energy, which is equal to force multiplied by displacement. That's why T1 multiplied by theta 1, which is equal to T2 multiplied by theta 2. Okay, so you get these equations. And this is the block diagram for the bicycle shown at the top. Okay, can you remember this formula? Okay, guys, are you sleeping? Everybody okay? Ihsan, okay? Sleeping. So this is the simple rotational system with gear. Okay, you have a mechanical spring damper. Then you have a rotational system connected between the gear 2 and gear 1. Okay, so the equivalent system at theta 1 at input N1, okay, is shown here. Okay, where the equations of the force, okay, is shown here based on the diagram here. Okay, so you can see that where the ratio of the gear 1 over gear 2 and the equivalent system at theta 2 at output N2 is shown here. Okay, with theta T1 over multiplied by N2 divided by N1 equal to the Newton's equation here, ds squared theta 2 plus ds theta 2 plus k theta 2. Okay, so we are using the standard formula here, theta 2 over theta 1 equal to N1 minus N2. So each of the gear system of N1 and N2 have their own equivalent system. Okay, theta 2 and N2, theta 1 and N1. So you are given an examples here. Find theta 2 over T1. Okay, so T1 is your input, theta 2, which is the rotation angular displacement of gear 2 is the output. Okay, so by referring to this part, okay, the equivalent system is represented by this diagram. okay, where the input T1, the viscosity damper PE, the inertia JE, and the spring KE, okay, which can be modeled as shown here. Input T1 and output theta 2. So the mathematical model between theta 2 and T1 is given by N2 divided by N1 over J square plus DE ds plus KE. Provided the value, the number of teeth of gear 1 and gear 2 is given. There is one example here where you are required to find the theta 2 over Ts for the rotational mechanical system. Okay, so the answer is given as 0.5 over S squared plus S plus 1, right? And the solution is shown here. Okay, so transforming the network to 1 without gears by reflecting 4 Newton meter radiant spring to the left and multiplied by the number of teeth 25 over 50, okay, N1 and N2, then square. So we obtain the equation of motion here, okay. So since everything is value equal to 1, so everything multiplied by 1, you will get back that value and use the concept of, first you factorize this one first, theta 1 and theta A, okay, by constructing a matrix. Theta 1 and theta A, okay, and this value is the matrix value from the equations here, and from there you apply the determinant formula matrices, okay, here, and then you will get the theta A over T, which is 1 over S squared plus S plus 1. But since theta 2 is equal to 0.5 theta AS, so you just include the theta 2, this constants, so become 0.5 over S squared plus S plus 1. Okay, so I show details here for you to refer. Okay, guys, so I stop here for today's lecture. We will continue back on Wednesday, which is 10th of November. Okay, 10th of November. Everybody okay? Hello?
Okay, Prof.
Okay,
So I
Doctor.
see you
Doctor.
on Wednesday. I will share you the link afterwards. Okay. Thank you very much.
Thank you, Doctor. Thank you, Prof.
Hello.
You
Hello.
Prof.
Hello.
Okay, Prof.